Take the quadratic equation, x squared plus 1 equals 0. If you try to solve this on the standard real number line, you hit a wall. Square any real number, and the result is always positive. The math stops. To bypass that barrier, we rotate the axis 90 degrees. We leave the single dimension of the real line and enter the complex plane. Under this new geometry, the roots of that equation exist at positive and negative I. We can formalize this beyond a single example. A complex polynomial is a sequence of terms where a variable is raised to integer powers, and every coefficient attached to those variables can be any complex number. This leads directly to the standard of algebraic completeness. A number field is considered algebraically complete if every non-constant polynomial within it has at least one root, meaning the equation equals exactly 0 at some specific input. By stepping from a one-dimensional line into a two-dimensional plane, equations that were algebraic dead ends now operate in a system where solutions are guaranteed. The challenge is proving that guarantee rigorously. We need to demonstrate that the complex number field is algebraically complete. For that, we turn to Walter Rudin's principles of mathematical analysis. Rudin addresses this in Theorem 8.8. He states the Fundamental Theorem of Algebra as finding a complex number z where the polynomial evaluated at z equals 0. Although this is a theorem of algebra, Rudin does not use algebraic manipulation to prove it. He uses analysis, the mathematics of limits, continuity, and topology. The core metric for this proof is the modulus, the absolute value of the polynomial, which measures its distance from 0. To find an exact algebraic root, we will treat the equation's modulus as a continuous three-dimensional geometric surface and analyze its limits. This visualization shows the modulus of a polynomial. The flat base is the two-dimensional complex plane, and the height represents the magnitude of the polynomial at any given point. Look at the macroscopic behavior. As the input value moves far from the origin, the highest degree term of the polynomial dominates. This pulls the surface upwards toward infinity on all sides. Because the terrain rises infinitely high along its outer edges, the lowest point of this surface cannot exist infinitely far away. It must be trapped somewhere in the middle. In topology, we define this finite, bounded region of the complex plane as a compact set. We then apply the extreme value theorem. Any continuous function operating on a compact set must achieve an absolute minimum value. Rudin defines this guaranteed lowest elevation as the value mu. By utilizing topology, the task of finding an algebraic root is narrowed down to investigating this single guaranteed lowest point on the terrain. The proof proceeds by contradiction. We assume that this absolute lowest point is strictly greater than 0. If the lowest point on the entire surface is above the floor, it means the polynomial never intersects the axis and no roots exist. To test this, we shift our mathematical frame of reference. We translate the coordinate system so this hypothetical minimum sits at the center of our view, and we normalize its height to exactly 1. Rudin formalizes this normalized, centered view by introducing a new polynomial, q of z. After shifting the origin and normalizing the height, the first term of this new polynomial is 1. We then identify the very first non-zero coefficient that appears in the expansion, which Rudin labels bk. We are now positioned at what is assumed to be the absolute bottom of the valley. If that premise holds, no localized operation should allow us to step further downhill. We analyze the local behavior immediately surrounding this point using that non-zero coefficient bk. This complex coefficient represents a fixed vector, pointing in a specific geometric direction. The proof identifies an angle, theta, that forces our variable vector to perfectly oppose that fixed coefficient vector. Translating this algebra into geometry, we take a microscopic step in the exact opposite direction of the local slope. We then evaluate the resulting magnitude of the polynomial at this new position. Rudin reveals the resulting inequality. The magnitude of the polynomial is now strictly less than 1. We have moved downwards. This creates a logical contradiction. We have walked downhill from a location that was defined as the absolute lowest possible point on the surface. Because a downhill path always exists whenever the surface is above 0, the true absolute minimum cannot exist in the air. It must rest exactly on the 0 floor. Local polynomial geometry ensures a path downwards. Therefore, the lowest point cannot remain above the axis, proving a root must exist. The immediate consequence of this theorem is factorization. Since at least one root is guaranteed to exist, we can mathematically divide the polynomial by that linear factor. That division yields a new, smaller polynomial, which must also have a root. We divide it again, creating an inductive loop that fully dismantles the equation. The conclusion is that every complex polynomial breaks apart completely into linear components. This theoretical guarantee underpins several applications across the applied sciences. Engineers rely on polynomial factorization to locate system poles. By finding these roots, they can calculate the stability of control systems, from aviation autopilot to electrical grids. In quantum mechanics, the completeness of the complex field ensures that operators have well-defined eigenvalues, which correspond to observable energy states. Physical models of reality require this theorem to avoid mathematical gaps in their predictions. Rudin's proof shows how these algebraic laws are established by mapping the continuous limits of a geometric surface. If you want to continue exploring the mathematical architecture of the physical world, subscribe to the channel and turn on notifications for our next breakdown. The complex plane provides a setting where algebraic limits are resolved by the laws of topology.